Alright, in this video I'm going to talk about partial differentiation, the remaining topic in chapter 7. So there are some additional topics in that chapter such as applications. We already discussed some applications of differentiation rules. So I think we are we had enough discussion about applications. And there is one more topic, Jacobian, in that chapter. But Jacobian is a much more important in optimization theory. So let me postpone that to part 4. So we are going to come back to Jacobian when we study optimization theory. All right, so let me illustrate the basic idea of partial differentiation in this video. So far, we studied the derivative of functions with a single variable. So function depends on just one variable, and this kind of function specifies relation between these two variables. We have just one input, okay, and one output, right? And then the relationship between these two variables is specified by function f. Okay, but this is not the only function that we study in economics. We've seen already, one example when we study the market model. Even in that simple model, so we assume linearity between price and quantity, but it turns out that price function, so equilibrium price, is a function of several variables. So in most economic models, many variables, many parameters are entangled each other. So now in this section we are going to study how to disentangle such many parameters in economic models. So it is most likely that we encounter the situation in which several parameters appear in the model. And this section, I'm going to introduce multivariate calculus. So how to analyze functions with multiple variables. So now function has not just one input, but several inputs, and then it yields some kind of output. And then we study how to extend the concept of the derivative we defined for single variable function into multi-word. Okay. So remember that derivative of a function measures, so if x changes a little bit, so when we change x just a little bit, so when we consider tiny change in variable x, what is a corresponding change in y? Okay, so it is an instantaneous rate of change. So if the derivative of a function is a 3 at some point x naught, it tells us at this point x naught, if we change x a little bit, okay, then the corresponding y will change by 3 units, will increase at the rate of 3 at that point. Okay, so yeah, there are several ways to interpret the derivative, and we studied how to compute the derivative for many different types of functions, and then how to interpret the derivative as a instantaneous rate of change. All right, and then we are going to extend that concept to functions with multiple variables. Okay. So in order to develop some idea, let me start with some simple function. So here the function f of x and y depends on now two variables, x and y. Okay, and then output denoted by z. Okay, so now in order to graph this function, we need a three-dimensional space. So here is the graph of this multivariable function. Okay, so the way to read this graph is this axis, this almost horizontal axis is for variable x. Okay, and another axis on the plane, on the same plane, this one is for variable y. And then vertical axis is for output z. Okay, so along this axis, okay, so if we change the variable along this axis, then y component does not change at all. Okay, So if we just slice this graph along this axis, okay, then we're going to have this parabola. That is a x squared. So in fact, if you put in 0 for y, the function collapses down to x squared. So we have this U-shaped parabola along this axis. Okay. Now if we change the axis to this one, so along this one, x component does not change at all. Okay, only y variable changes. So if we let just y change, okay, then x is a constant. Then, some constant minus y squared. So if we slice this graph, in this direction, or, if we project this graph into this plane, then we're going to have this upside down graph that is a upside down parabola that is a some constant minus y squared. Okay? But, it is self-evident from this graph that output z now varies with, both x and y. As x and y change, output z also changes. Okay? So here, the idea of, considering corresponding change in z in response to change in x and y, originally, both x and y will influence output z. Okay, but first we block this channel. Okay? We block this channel, and then we only consider what is a corresponding change in z in response to a change in x. Yeah, although two variables, x and y, can change, okay, but we do not consider change in y. Okay, only consider change in x. That is the basic idea of a partial derivative. Okay, so we change one variable at a time, keeping the other variable constant. Okay, so even though the original function is a function of two variables, we first regard that as a function of a single variable, okay? And thereby, we consider partial variation of function, okay? So the function z or f can change in response to a change in x and y, but we do not consider this change, okay? So only see the direct effect of change in x on function's variation. So that is a partial variation, and we are going to see the total variation of function f in chapter 8. Okay? So then this partial variation can be expressed as, so now y component is fixed by some constant y naught. It does not change at all. Okay? So only we increase x just by h from x naught to x naught plus h. So that is going to be partial variation of function f in response to a change in x. Okay, so we put this quantity on the top and put the change in x on the bottom, and this ratio is defined as the partial derivative of f with respect to x. So after taking the limit as h goes to 0, that is an instantaneous rate of change in response to a change in x only. So that is called partial derivative of f with respect to x. Okay, so for partial derivative, we use a special notation. So that is a curly d, like this one. So instead of a standard d, dz over dx. Okay, so that is a standard differentiation, but for partial differentiation, we use this curly d, okay, and is read partial. So partial z over partial x stands for partial derivative of f with respect to x. Okay, and because function also depends on y, we can consider partial derivative of f with respect to y. Okay. And definition is pretty analogous to the previous one. So now partial derivative of z with respect to y, that is defined as the instantaneous rate of change in response to a change in y. Okay, so now we regard x as a constant. So we treat our variable x as a constant. Okay, so x does not change at all. We increase y just by h. Okay, and then the difference between these two measures a partial variation of the function f in response to a change in y. Okay, and then we divide it by increment of y, that is h. Okay. And then take the limit as h goes to 0, so instantaneous rate of change of function in response to a change in y. Okay, so that is a partial derivative of f with respect to y. Okay. So whenever a function has two variables, we can define a partial derivative with respect to the first variable and the second variable. Okay? And then this partial derivative often denoted by subscript. So if function depends on x1 and x2, then the partial with respect to the first variable, so treating x2 as a constant, we just change x1 and then see corresponding change in function, that is a partial with respect to x1, denoted by f sub 1. Okay, similarly, partial with respect to the second variable, f sub 2. Okay, if the variables are letters like a u and v, then partial with respect to u is going to be f sub u. Okay, that is partial f with respect to u, and f sub v is going to be partial with respect to v. All right? And then the way to compute the partial derivative is a piece of cake, because now let me compute f sub 1 in the first example. So partial derivative with respect to x1, meaning that we regard x2 as a constant. This one is a constant, this one is a constant. Okay? Only x1 is a variable. Then the derivative is, we just borrow the same differentiation rules we studied in the previous lecture. So 3x1 squared becomes 6x1. Okay? And then, we regard the x2 as a constant. And that constant is multiplied to variable x1. So that will be x2. Okay, so x1 becomes 1, and we leave x2 because that is a constant. Okay, and then 4 times x2 squared, now that is a constant, so it goes away after differentiation. All right, so that is f sub 1, and f sub 2, now partial with respect to x2, now we regard the x1 as a constant. Okay, so this one is a constant, and this one is a constant. All right, so after differentiation, 3x1 squared goes away, and this x1 multiplied to variable x2, so leave it alone, and the derivative is just x1. And then for x2 squared, the derivative 8 times x2. Okay, so that is f sub 2. Let me do one more exercise. So the second example, now function depends on two variables u and v. Okay, and then if we consider partial with respect to with respect to u, now we consider v as a constant. So now this one is a constant. All right, and still we have a product of two u functions. So now using the product rule, derivative is the derivative of the first function, that is 1, and then we multiply it by the second function, and then the first function multiplied by derivative of the second, that is just a 3, right? Because 2v is a constant, so it goes away. So I don't like a simplification, but This is a very simple algebra, so let me do that. 3u plus 2v plus 3u plus 12. So we obtain 6u, 2v, 12. Okay, now with respect to v, okay, and then this one is a constant, u plus 4. So u is a constant, 4 is originally constant, and 3u is also constant. Okay, the only variable term is a 2v. Okay, so with that in mind, now the derivative is, because now this one is a constant, so this is just a constant multiplied by some function of v. So we just leave a first term, u plus 4, because this constant is multiplied to function of v. Okay, and then we take the derivative of the second term with respect to v. So 3u goes away, and we just left with 2. We are just left with 2. So 2u plus 8. Okay, so that is a partial derivative. And for this one, you may have to use the quotient rule, because we have a function of u and v on the top, and another function of u and v on the bottom. But you can find the partial derivative in the similar way. All right. So, all right. The basic idea of a partial derivative is, although original function depends on two variables, we block one channel like this. Okay. So the way to justify this analysis is, whenever two variables are, your choice variables, you choose x and y. Okay. So that means there is no interdependence between x and y. You choose x and y independently. Okay. In such a case, there is no relationship between these two choice variables. So in such a case, this partial differentiation analysis can be justified. But if there is a high interdependence between these two, so whenever x changes, y also changes. Okay? If y is a function of x, this analysis has a no ground. So in that case, we have to consider a total variational function instead of partial variation. But in economics, think about a firm. Okay, you are an owner of some firm, so you have to decide how many people you employ and how much capital you borrow from bank. Okay, and these two variables will decide the quantity produced, how many units you will produce. Okay, so in economics, we regard one firm as one production function. So production function tells us given inputs, so the number of people you employ and the amount of capital you borrow from bank, that decides, so that determines the quantity produced. So we consider a firm as a unit or institution which has some technology transform input to output. Okay, so firm is often described by some production function in economics. Okay, but anyhow, these two variables are choice variables. Okay, so in such a case, partial derivative has an economic meaning. Okay? So specifically, if we graph this function, now it will be some three-dimensional shape like this. So here we have an origin, and then we increase capital or increase number of people. Okay, and intuitively, if you hire more and more people, or if you employ more and more capital, the amount of quantity you produce will increase like this. Okay, but if we consider partial derivative of this function with respect to L, okay, that is called marginal product of labor, okay, and its economic interpretation is you just hire one more people, then you can increase quantity produced, And then this MPL measures that incremental quantity. Okay, so once again, if you hire one more people, the quantity produced will increase, right? Because you just hire one more input, right? So that incremental quantity is called MPL. So marginal product of labor. Marginal product of labor. Okay, so if that is a 3, that means you hire one more people, then you can increase quantity produced by 3 units. Okay? Right, so that is MPL. And similarly, if we take the derivative with respect to K, we obtain marginal product of capital. Okay? Once again, the interpretation is if you borrow one more dollar from a bank, so you increase amount of capital just by 1 unit, then what is the corresponding increment of quantity produced? That is MPK. Right? So, when we analyze firms' behavior, we start with some production function, and its partial derivative with respect to each input has some economic meanings. Okay? MPL or MPK. And for analysis of consumer, we start with a utility function. So consumer can choose good 1 or good 2. So here x1 and x2 are choice variables for consumer. Okay? So x1 stands for demand for good 1 and x2 demand for good 2. Okay? So once again, these are choice variables. So disregarding interdependence between these two, we can consider partial derivatives. And its economic meaning is called the marginal utility. So if we take this utility function and take the partial derivative with respect to x1, then we call this partial derivative marginal utility from good 1. Its interpretation: if this consumer purchases 1 more unit of a good 1, okay, then the level of satisfaction utility will go up, right? So this mu1 represents that measures the increment of utility from additional purchase of good 1. Okay, that is mu1. And mu2 is defined as the partial derivative of a utility function with respect to x2. Okay, interpretation: now the consumer purchases 1 more unit of a good 2. Okay, and then x1, the demand for a good 1, is a constant. It is held, by some. So it is fixed by some constant. So it is held constant. Okay, so just increase the consumption of a good 2 by 1 unit, and the increment of utility from that is called the marginal utility from good 2. Right? So in these two cases, partial derivative have some nice economic interpretations. Right? So let me do just one more exercise. So now the production function is specified by this Cobb-Douglas function. This is called the Cobb-Douglas in economics. Cobb-Douglas. So if you study intermediate micro or intermediate macro in both disciplines, you will see this type of function several times. Okay, so it is given by 100. That is a constant, the arbitrary constant. Okay, the Cobb-Douglas indicates the square root of L times K. Okay? A general form of Cobb-Douglas is L to the power alpha and K to the power 1 minus alpha. Okay? And then so this corresponds to the case when alpha is given by 1/2, because the square root of LK is LK raised to the power 1/2. So distributing 1/2 we have L to the 1/2, K to the 1/2. Okay, so that is one example of Cobb-Douglas. Okay. Anyway, we can compute the marginal product of each input. So let me work with. So let me first translate function to 100 L to the power 1/2, K to the power 1/2. Okay. Now let me compute MPL. MPL is partial derivative of this fraction function with respect to L. Okay, so now we regard K as a constant. Okay? So in this case, if we just take the derivative of L term, then power 1/2 comes up front, and we take 1 away from the power. So the new power becomes negative 1/2, and then K term, because that is a constant and is multiplied, so we just leave it alone. So that is MPL. Okay. Then let me simplify this. 50 and K to the 1/2 over L to the 1/2, because whenever we have a negative sign in the power, we can move it to the bottom by changing the sign of the power. Right? So we have this, and then we can rewrite this 50 square root of K over L. Okay, there is MPL. And now compute MPK. So MPK is partial with respect to K. Okay, so once again, let me work with this function. And now L is a constant, right? So leave the constant terms alone. And then we take the derivative of K to the power 1/2. So 1/2 K to the power negative 1/2. So 100 times 1/2 gives me 50 L to the 1/2 K to the power negative 1/2. So I can rewrite this 50 times square root of L over K. Okay. So if we evaluate the marginal product at 1,4, so currently you hire 1 people and you borrow 4 units of capital, then this number is going to be 50 times square root of 1/4, so 25. Okay, so MPK at that point turns out to be 25. It's economic interpretation. If you employ 1 more unit of capital, you can increase your quantity produced by 25 units. Okay, and MPL at that point is going to be 100. Right? So it's interpretation. If you hire 1 more people, then you can increase quantity produced by 100 units. Okay, so at this point, labor is much more productive, actually 4 times more productive than capital. Okay, and then for utility function, so this type of utility function is called quasi-linear utility function, because we have 2 variables, x1 and x2. With respect to x2, that is a linear. But with respect to x1, that is a non-linear. So this type of function, we call that quasi-linear utility. Okay? So if we compute marginal revenue from each good at 4,10, so the consumer currently consumes 4 units of good 1 and 10 units of good 2. Okay, at this point, if we compute marginal revenue, so mu1 is partial derivative of u with respect to x1. Okay, now x2 is a constant. So we just take this part and take the derivative, and we obtain so 4 times, it's very convenient to remember that square root function's derivative is 1 over 2 times the square root of x. Okay, so now variable is x1, so we have a square root of x1. So we have a 2 over square root of x1. Okay, so at 4, 10, so because there's a no x2 in this expression, so we just put in 4 for x1 to obtain just 1. Right? So interpretation, if this consumer consumes 1 more unit of a good one, and his utility or her utility will increase by 1 unit. Okay? And similarly, mu2 is just 1, right? Because now the first term is a constant, and the derivative of x2 is going to be 1. So regardless of the current amount of consumption of good 2, okay, her utility or his utility, this consumer's utility will increase by 1 if she or he consumes 1 more unit of good 2. Okay? So that is a application to economics, the application of partial derivatives to economics. And finally, there's one more topic in chapter 7, there's a gradient. So the gradient is nothing but the set of partial derivatives. Okay, so suppose that we have we have a function f depending on 2 variables. Then we can compute the partial with respect to x1. That is a 1 partial derivative. We can derive from this function. And then the other partial derivative with respect to x2. And then collection of these partial derivatives is called the gradient. Okay? And then gradient is denoted by this upside down triangle f. Okay? That is called the gradient of function f. Okay? So this is just a slight extension of partial derivative. So the only skill we need for finding gradient is it's the same as before. So the way to find the gradient, problem of finding gradient is the same as finding all partial derivatives. Okay. So for example, if we have a function depending on x1 and x2, then partial with respect to x1 is going to be 2x1 times x2, right? Because x2 is a constant. Okay, so x1 squared, the derivative is 2x1. And partial with respect to x2 is going to be x1 squared. Okay, so the gradient is going to be 2x1 x2 comma x1 squared. Okay, now we have a function depending on 3 variables, but does not matter. Now we have a 3 different partial derivatives. Now the variables are denoted by x, y, z. So the first partial will be with respect to x, second with respect to y, third one with respect to z. Okay, so the first one is 2x, because y cubed and z to the power 4th are constant and they are added. So we can just delete these 2. And then partial with respect to y, that is a 3y squared. And finally, with respect to z, that is a 4y cubed. Okay, so if function depends on 3 variables, we have 3 elements or 3 entries in the gradient of function. Okay, so collection of all partial derivatives is called the gradient. Right? So this is a very important. So this is, it plays quite pivotal role when we study optimization theory. So if we just evaluate each partial derivative at some specific point, just as we evaluate the partial derivative at some specific point in the previous example, if I evaluate this one, say 1, 1 at 1, 1, so when x1, x2 are equal to 1, then this gradient is going to be a vector, 2, 1, okay? And then it has a very important meaning in optimization theory. So we are going to come back to gradient in the last part. All right, so I think this is the end of chapter 7. Hope you guys enjoyed this video. And if you guys have any questions, don't hesitate to send me an email. All right?